Okay, so now we're going to go through the menstrual cycle, and as we go through it, we're going to emphasize gametogenesis and folliculogenesis, okay? And we're going to try to talk about how the oocyte develops and gets ready for fertilization and is fertilized. And at the same time, we're going to talk about how the follicle around it develops. And then, once again, we'll go through this again in the next section, but we'll emphasize hormonal changes at that point. So let's talk about gametogenesis a little bit. The whole process starts with the primordial germ cells here in both the male and the female. And we're going to talk about a lot about the male in this lesson, but in both sexes, basically, this development of either sperm or oocytes is characterized by mitosis, by which the germ cells become oocytes or oogonium, and in the female. And then this in both sexes will be followed by 2 rounds of meiosis, which eventually produce either the ovum or the sperm. Okay. Again, in the female, starting at about 20 to 24 weeks of fetal development, you have embryonic mitosis taking place where your germ cells become oogonium. And then at about 8 to 9 weeks of fetal development, you have the first meiotic division starting. And notice that this meiotic division does not complete. It's arrested partway through at the diplotene stage. And we call the oocyte at this stage the primary oocyte. So this is happening during fetal development and for at least a little while after birth. And as we'll find out in a moment, these are surrounded by primordial follicular follicles, or contained within primordial follicles. And so we have these oocytes, they're lined up, they're ready to go. They're arrested partway through the first meiotic division. And you should note that the process of attrition begins also at about 8 to 9 weeks fetal development. So there are 2 million oocytes at birth. By the time you hit puberty, it's down to 100,000 to 400,000. And as I said before, there's only a small fraction of these that actually get ovulated. So this is taking place because there are no gonadotropins. The gonadotropins are low during childhood, and the development of the follicles in the oocyte can't take place. So they shrink up and die. Starting at puberty, what happens is you have all these follicles and all these oocytes. They're lined up and they're ready to go. And through a process that is not completely understood, a number of them are selected to start developing, okay? And so this happens in a cyclical manner. It's, they're selected during the follicular phase of whatever cycle that you're in, if you're a female. And this cohort of follicles begins to mature, and eventually they degenerate in this cyclical manner post-puberty, the menstrual cycle, okay? So the first meiotic division resumes as these follicles mature around the oocyte, and the first stage of meiosis completes like a day before ovulation. So when ovulation takes place, the first meiotic division has just completed, and the second meiotic division has begun, and it is arrested at metaphase 2. So the second meiotic division is arrested as when this oocyte is traveling down the fallopian tubes. Okay, that meiotic division will not complete unless fertilization takes place. Should that take place, the second meiotic division will complete, and the magic of genetic recombination will take place. So notice with this first, the completion of this first meiotic division, we have this oocyte And this polar body forms when that meiotic division takes place. And what happens is half the genetic material ends up in this polar body, and half remains in the main part of the oocyte. So this is like trash. It'll no longer be used. It shouldn't be fertilized. And the same thing happens again when the second meiotic division completes. You form a second polar body, but the embryo is going to develop from the big oocyte here that has what's left of the genetic material recombined with the male genetic material contained within the sperm. Okay? This is a, quote, ovary. Note that it is a cartoon. It is not a histology slide. The histologist will gladly show you these slides of this. This is just a cartoon to demonstrate, generally speaking, sort of an overview of how follicles develop around these oocytes. Notice that the follicles are surrounded by granulosa cells here, and these will reproduce, and the follicle will become very large as it develops, primarily, mostly, though not entirely, because granulosa cells proliferate. And this is the oocyte here in the center, okay? So we start with the primordial follicle, and the primordial follicles are transitioning to primary follicles, which transition to secondary follicles throughout life, okay? These stages can take place in the absence of gonadotropins. They take place pre-puberty. They take place post-puberty, okay? And you are developing secondary oocytes all the time. However, in the absence of gonadotropins, these follicles are, the oocytes and the follicles are going to undergo atresia, and they're going to waste away. They are not going to develop into anything that might ovulate. So the number of follicles decreases quite a bit, as I told you earlier, because these follicles can't transition past the secondary follicular phase. Okay? Post-puberty, when gonadotropin is present, you get, as the female cycle takes place, transition from 2 to 3. That is, transition from the secondary follicle to the mature follicle, also known as a Graafian follicle. And, of course, the first meiotic division takes place right before this ovulation. That takes place, it finishes right before, it starts before, it started already in the secondary follicle. It's partway through at this point, and then it completes right before ovulation, and you have ovulated with a oocyte that has completed the first meiotic division, but not the second meiotic division. The second meiotic division freezes partway through. Okay, so here's your oocyte surrounded by a corona radiata. We'll cover what that is in a second. And here's your ovulated remnants of your follicle, Graafian follicle. So the oocyte exits, and if it's fertilized, the second meiotic division completes, as I demonstrated on the previous slide. And the corpus luteum follows ovulation and develops, and these are follicular cells which have undergone a transformation into a type of cell which does a very good job of secreting progesterone, which is very important during the luteal phase of the cycle, along with some estrogen, okay? And then this corpus luteum, if pregnancy does not take place, degenerates, becomes a corpus albicans, and you have this atritic follicle, which is basically a scar on the ovary, okay? So, once again, stages 1 on this is just the same cycle in more detail. 1 through 4 is the development of the primary and secondary follicle. These stages do not require gonadotropins. They take about 200 days total. They happen throughout the life of the female. There is a big increase in size during this phase. We start with about 600 granular cells here, granulosa cells. by the time you become a secondary oocyte, you've got 75,000 of those cells, so this has increased already quite a bit, okay? And then 47 million here in the mature follicle at stage 8. Let's take a look a little bit more at the development during these stages. So here's our primordial follicle. The early primary follicle develops when the granulosa cells become cuboidal and start to mature. And you can see the development of what's called a zona pellucida here. That's a layer, a mucus layer that develops inside, and it forms a barrier between the oocyte and the granular cells, okay? And it's generated by the granulosa cells. A little bit later in the development of the primary follicle, we have the development of the theca interna. These are stromal cells that differentiate into cells that might mainly produce androgen, and that androgen goes from the theca internal cells into the granulosa cells and is turned into estrogen, okay? And the granulosa cells develop protrusions. You don't see it here, but they help provide nutrients to the ovum. We have the development of antrums as the secondary follicle forms. These are spaces in between the granulosa cells here. These can contain liquid, which is generated from the granulosa cells. Eventually, these will all coalesce into the liquor of folliculi in the mature oocyte. And notice the development of the theca externa now, which is outside the theca interna. It's a hard fiber shell, protects this follicle as it's gotten very big and starts to fill with liquid. And we also have the development of the membrana granulosa from the granulosa cells. This forms a barrier between the granulosa cells and the liquor of folliculi, which is here, all this liquid-filled space. And it contains a variety of different hormones which help the oocyte development. We have the development of the corona radiata. These are granular cells which surround the oocyte, and that is connected to the follicular cells around the outside by the cumulus oophorus here, which is just like a neck of granulosa cells. At this point, the oocyte is being held in place and it's getting ready to be ovulated, okay? So these last stages, secondary through production of the Graafian follicle, happen under the influence of these post-puberty hormonal changes. And we're going to talk about that a lot in a minute. A lot of follicles are recruited at stage 5, but during the progression and maturation process, one is selected. We'll talk about that in a moment, how that happens. There'll be one follicle out of both ovaries that will be selected and will ovulate. Okay, that takes place here. So estrogen is very important for the development and maturation of these follicles, as you're going to find out a little bit later in the lesson. And again, it's made through cooperation between the thecal cells and the granulosa cells. So you will notice that we have our thecal cell here in the theca interna. It is binding LH, luteinizing hormone, and that is causing the production of androstenedione and some testosterone. Okay? Androstenedione is an androgen, so we're talking about androgens that are precursors for estradiol. The androstenediol goes to the granulosa cell, okay, through diffusion, and then that is converted through the auspices of aromatase, which is stimulated by FSH, to testosterone, and then through the auspices of aromatase to estradiol, okay? And the estradiol is secreted into the into the follicle and also into the bloodstream, where you will find it increases during follicular development. Okay, and that is this section as well. The estrogens are important in this process of development of this follicle. Okay, what's happening is estrogen is producing more granulosa cells. It's stimulating the production of more granulosa cells, which are primed to produce more estrogen. And not only that, it increases the synthesis of more estrogen receptors, which in turn stimulate the production of more granulosa cells. So what you've got here is proliferation of the granulosa cells through the auspices of estrogen. And this is a positive feedback loop, as we will see in a second. Estrogen causes the production of more granulosa cells, which produces the potential to produce more estrogen, okay? Because the more granulosa cells you have, the more estrogen you can produce and secrete, okay? And again, it's estrogen that is, it is estrogen that is driving the process of development of these follicles, okay? The estrogens, along with the presence of FSH, drive the appearance of LH binding sites in the granulosa cells. That produces more androgen, which feeds in to help produce more estrogen as well. So again, a positive feedback process here, okay? Estrogen, important to the development of the follicle, important for a lot of reasons. It alters the cervical mucus. It becomes kind of thin and watery, less acidic, and so it's easier for sperm to penetrate. It relaxes the cervix a little bit as well. It begins peristalsis in the fallopian tubes, so that more movement of the fimbria, and the endometrial layer proliferates and begins to prepare itself for potential implantation of a fertilized ovum as well. All of this takes place under the auspices of estrogen. We'll talk about that in a minute, a little bit more later in the lesson. Estrogen is also responsible for the selection process of the dominant follicle. So estrogen inhibits the growth of the cohort follicles, and what it's doing is it's decreasing the secretion of FSH, okay? So FSH is needed to produce estrogen. It stimulates granulosa cells to produce more estrogen, and at the same time there is a negative feedback loop that I've shown you previously. Estrogen feeds back on the hypothalamus and the anterior pituitary, and it decreases FSH production. This negative feedback loop keeps the secretion of estrogen under control, okay? Despite the fact that the granulosa is proliferating, it's kept under control by this negative feedback loop on estrogen. Well, what happens is estrogen produces more granulosa cells. So what the dominant follicle is thought to be the one with the most FSH receptors. That is the one that can respond to make the most estrogen and therefore proliferate the most granulosa cells at the lowest level of FSH, because FSH levels are decreasing through this negative feedback loop and this inhibition. So you've got low FSH, and the dominant follicle is the one that's able to take the FSH that's there and produce the most estrogen and therefore proliferate and make the most granulosa cells. So that becomes the dominant follicles. The rest are inhibited and they undergo atresia, okay? And you end up with this one follicle with the most FSH receptors. It's thought to have the most FSH receptors that's selected for ovulation, okay? During this phase, the LH stores are increasing in the anterior pituitary, and that, as you will find out in a second, is going to be used in what's known as the LH surge, which takes place right before ovulation. And it also primes the hypothalamus to prepare for a larger GnRH release, okay? So we're going to eventually get a switch in this feedback loop from this negative feedback loop, which is keeping FSH and to a certain extent LH under control, to a positive feedback loop where estrogen is going to cause an increase in particularly LH secretion, and that's going to cause what's called an LH surge, and that's going to be essential for ovulation. So estrogen is helping to prepare for that LH surge as well, okay?